Good morning, everyone. We have still some people joining, but I will start because we have a very, very tight schedule. So people will catch up as they arrive. So thank you so much for joining this morning. It is a pleasure to meet you all today. My name is Clémence Priken. I work at FEDAREN and I am part of the RELaTED project team. And today we're having a wonderful webinar, short but very interesting, on solar energy solutions for decarbonizing district heating. This webinar is recorded. Some guidance already. I'm asking you to turn off your camera if you are not speaking, and if you have questions for the Q&A later on, you can use the chat box. So that we can get all the questions and it would be a bit easier to manage. The agenda of today, we will first welcome Ms. Eva Hoos from DG ENER, who will tell us more about the EU renovation wave. Then you will have a presentation of the current state of RELaTED done by Mr. Christian Christiansen, and then at last, you will have a presentation of the WEDISTRICT project, by Mr. Jose Arjona. I will first invite on board Mr. Mrs. Eva Hoos. I'm sorry. This is stress of the starting. I will stop sharing my screen, and Mrs. Hoos, you can start sharing yours if you're ready. Yeah,
good morning. I will try to bring on screen my presentation, if I can. I have to.
We can see you and the wonderful background you have.
So I am sorry, I have a bit of. Okay, so try to. Sorry. So good morning, and I will have to do a screen sharing. Can you see my screen now?
Yes.
Yeah. So good morning, everybody, and it is a pleasure to be here this morning and discuss the renovation wave, but also to hear about the project that you are doing. So as a matter of introduction, I would outline a bit the EU policy background that is also the background for the renovation wave, and what are the key aspects that this communication was looking at, and what is going to be the follow-up for the renovation wave. So as you probably well know, the strategic overarching policy framework has been given in the European Green Deal. That was one of the first action the new Commission led by President von der Leyen has been made. And this basically aims to speed up the transition to a green and digital economy with the ultimate objective to make Europe the first carbon neutral continent on the globe. Then the European Green Deal has been, the energy-related component and goals have been reinforced in the climate target plan that was published last September, which basically aims to achieve 55% greenhouse gas reduction already in 2030, that thereby increase the target from the current 40%. And this new, more ambitious greenhouse gas reduction target has been endorsed by the European Council and the European Parliament. The European Green Deal has also fostered a number of important strategies and communications that lay out the main principles how such green transition should be implemented. And these are the energy system integration strategy that was published last July, the hydrogen strategy adopted at the same time, and the renovation wave that was published in October last year. As a result of the European Green Deal and all these detailed strategies and communications, the Commission is now preparing a legislative package, because obviously there is a need to update and adjust the market and regulatory framework to make possible such decarbonization, because it basically implies a radical transformation of our energy system, the way we produce and consume, the energy carriers and all the end consumer sectors, out of which the biggest one is the European building stock. So the renovation wave has been adopted in last October, and this recognizes the importance of the building stock, which 85% of which it was built before 2001. So that means basically before any energy performance requirements have been applied, at least at EU level, even if some member states already had such type of regulation legislation in place. As a consequence of the 55% emission reduction target already in 2030, there is a need to reduce buildings' greenhouse gas emissions by 60%, their final energy consumption by 14%, and within this complex, the energy consumption for heating and cooling should be reduced by 18%. The key messages of the renovation wave is that there is a need to increase the renovation rate of the building stock, which currently is around 1 percentage point as a overall average. Obviously, there are segments of the building stocks and also countries or regions where there is a high renovation wave, but overall that's very low, 1 percentage point. And if we go with that rate, then building decarbonization is not going to be achieved really in the next 100 years, or even it would take longer to do that. So there is a need to increase the renovation rate of buildings to at least double what we have today, possibly even higher. And such renovation, speeded up renovation should continue beyond 2030 and up to 2050 to contribute effectively to the Green Deal objectives. A corollary of this deep renovation and the stage renovation of the EU building stock is that we also need to replace the heating systems and the cooling systems in buildings, and it's not in the renovation wave, but in the climate target plan that we need to achieve at least a 4% replacement rate annually to switch buildings' heating and cooling systems from the current fossil-based and largely inefficient systems to something that will be sustainable. The key principles of doing this work is energy efficiency first, that has been introduced in the clean energy package as an overarching principle that should be mainstream in all EU energy policies and even wider in all EU policies. That means that instead of focusing on new production capacities, new networks, and the related investment, there is a need first to look at whether we can reduce demand or do production and consumption more efficiently. And then after this consideration, we can optimize how much new investment is needed in energy generation and energy transportation and distribution. A second important principle is affordability. Buildings are a big part of our lives and an important part of the value or wealth that citizens have. It's also an important component of our expenditure. So there is an important aspect of affordability and making sure that building renovation contributes to increased well-being and also doesn't result in income inequalities and more burden on the low-income segments of the population. Integration of renewables next to energy efficiency is very important. Buildings should be renovated or built in a life cycle thinking and circularity, meaning that the materials also needs to respect low CO2 and other emission reduction. Obviously, we need to keep high health and environmental standards, and the aesthetics and architectural quality should be preserved. So the key actions that the renovation wave has laid out relates to strengthening mandatory minimum energy performance standards, not just for new buildings, but also for existing buildings and for energy renovation of buildings. For this purpose, the energy performance standards should be reliable and transparent. There is a need to update energy performance certificates to be also reliable, transparent, and convey the messages for the building owners, flat owners, but also the professional bodies. What is the status of a given buildings or building unit and how it can be improved. The renovation wave has defined a number of priority areas for actions, and these are the public buildings that should be leading by examples. More focus should be given to social aspects and social housing, also in the view to reduce energy poverty and use building renovation for that purposes. Then it is a new element that there are more focus, more consideration of how district and community approaches and energy communities could be used to scale up and the building renovation, but at the same time also reduce the cost of doing this for the building owners and for the inhabitants of buildings. Tackling energy poverty is very important, and a key focus area is decarbonizing heating and cooling systems in buildings. So in this context, what is also perhaps important to highlight that the renovation wave, but also the other strategies that has been issued under the Green Deal, such as the energy system integration strategy, considers that district approaches and district heating and cooling can play an important role in decarbonizing buildings and also heating and cooling, because we have a big challenge on shifting the current large amount of fossil fuels in heating, which amounts to around 450, 500 MTOE. So that's really a vast amount, of which 2/3 is based on fossil fuels, including coal, heating oil, and natural gas. So it's not a minor challenge to decarbonize this vast amount of energy that constitute basically half of the European energy consumption to this new paradigm, and do it already, start to do this already in the decade that until 2030, and then continue more intensively until 2050. And this kind of district approach and the role of modern district heating and cooling has been going to be also an important aspect of the implementation of the renovation wave and the implementation of the other strategies. And first and foremost, that also means that district heating systems themselves should become much more Green Deal compatible, and they also have to modernize. The new systems that are going to be built should be fully based on the principles of energy efficiency and renewable integration, but also system integration in a way that they contribute to decarbonize the entire energy system by allowing more flexibility, by using renewable electricity, and helping optimize the energy system by also optimizing how renewables are used and how the carriers are used in heating and cooling, also allowing a connection between the heating sector, cooling sector, and the electricity sector, and the gas network and gas carriers, which also need to be decarbonized. So the follow-up of these strategies is basically a complete reshuffling or revision of the current legislative and regulatory framework. The first step is going to be the Fit for 55 package, which is reviewing a number of directives and regulations that are interlinked, so to really be able to tackle issues that are horizontal and have regulatory components in the Renewable Energy Directive, in the Energy Efficiency Directive. Also, there is a need to update the carbon, the EU emission trading frame system, and therefore sharing regulation and energy taxation. So that is these are the main relevant pieces of the Fit for 55 package that is planned to be adopted already this June. So it's basically next month to do the first stage of update for the market framework to ensure that market signals and carbon price signals are helping investment in this direction and in green, in the green transition, but also the regulatory framework. Now, as a next stage to that, there is going to be a review of the energy performance of buildings directive with many components in it, and then this will also be followed by the eco design and energy labeling framework update especially for space heaters and water heaters, to basically ensure a Green Deal compatibility of this regulation. So what is important also to highlight that all these market and regulatory frameworks are being updated, while at the same time there is an unprecedented amount of public money that is being made available for this work. The renovation wave actually provides a very detailed description of what kind of financing instruments and funds can be used for this very significant investment that has to be made in the building stock, in the heating and cooling systems, in networks, and so on. This spending has been mainstream in the new EU budget, but also the Next Generation EU and the Recovery and Resilience Facility that is linked to the COVID, how to overcome the economic crisis resulting from the pandemic. Altogether, we see a climate mainstreaming of 30, 35, and even higher for specific funds. That means that the EU budget and the Next Generation EU budget, which is around 750 billion euro, should be to a large extent spent to that kind of green and digital transition. So this is basically in a nutshell, that's obviously a very complex program to implement the renovation wave in the context of the Green Deal, but with many, many details that are going to be tackled in the Fit for 55 package and later on in the EPBD review. But this is how I could summarize in a nutshell.
Thank you so much. Thank you so much, Mrs. Hoos. It was indeed very interesting, very detailed. I'm sure that we will hear more in the coming weeks. I will kindly ask you to stop sharing, and to invite Mr. Christiansen to join me on stage. Meanwhile, if you have some questions, please use the chat box. It is there for you. I still hope we will make it for an interesting and full Q&A session. So don't hesitate. The floor is yours.
Thank you. My name is Christian Holm Christiansen from Danish Technological Institute, where I'm a senior consultant. We are part of the RELaTED project, and I will tell about some of our experiences and developments in this project regarding solar thermal for district heating. First, I will say a little about the RELaTED project, then something about catching the sun, and then how we deliver heat to the district heating network locally, and how we store the heat locally, and some perspectives of the RELaTED project. The RELaTED project is a Horizon 2020 project with 14 partners. We are addressing different district heating system needs, for instance, reduction of the operational temperature, which is also related to energy efficiency, introduction of larger share of renewables, introduction of distributed heat sources. This could be the kind of sector coupling we were talking about in the introduction, and then something about the viability of supplying nearly zero energy buildings. We are demonstrating solutions in 4 districts in 4 countries. Those are Iurreta in Spain. It's a small facility with a local network. Then we are demonstrating in Belgrade in the district heating system there. And then in Tartu in Estonia in their district heating system. And then we have a greenfield district heating system in Vinge in Denmark. which is also supplemented by some demonstration in a demonstration area we got at Danish Technological Institute. The project runs until mid-2022, and you can, of course, look at our website. One of the things we are dealing with is actually reducing the temperature. And we are trying to develop a scheme where we are supplying a temperature where applicable below 45 degrees Celsius. This means that we need space heating that can cope with such a low temperature. That's typically underfloor heating. And then we also get some challenges with domestic hot water when the temperature is so low. So we need to do a temperature boost of the domestic hot water, and that we can do by supplying district heating up to a certain temperature, and then boost with electricity with a heat pump for the rest, so we can have a decent domestic hot water temperature. The heat sources we are considering for the district heating system is industrial surplus heat. We are also looking at building integrated solar thermal. Then we are looking at reversible heat pumps, and the reversible heat pumps are heat pumps that can deliver cooling during summer, and then distribute the excess heat from the cooling to the district heating network. And then during winter, it can actually boost the temperature, either for boosting the supply temperature for space heating or domestic hot water. And we have some companies involved in the project that are providing both solar thermal and the reversible heat pumps and also substations. So we have a overall focus looking both at system architecture and subsystems, the economy, demonstration, and dissemination. Okay, so looking at catching the sun, one of the things is that many of the technologies we got are actually delivering heat at a low temperature, and they are actually also delivering higher capacity factor or higher efficiency if the temperature is low. And then when we apply low temperature, we also actually get some new design options for some of those technologies. If you look at the graph here on the right, here we are comparing the mean temperature of solar collectors. And if you go from a mean temperature of 60 degrees to a mean temperature of 45 degrees, you are actually increasing the yield you can get out of the solar collectors with, in this case, 36%. So we can get more energy out of it. Of course, it is energy at another temperature, but yeah, this is a way to increase the capacity factor. Then you can discuss if we should use built-in integrated solar heating or not. And what we're doing in the RELaTED project is that we are looking at some different solutions. You can have building integrated horizontal solar thermal, and this can actually be integrated in the building facade, so it also have an architectural aspect. And then you can of course have something on the roof, and if you look at this nearly zero energy building, then if you use the whole surface of the roof, then you will have about 50 square meters, and that is actually sufficient to deliver quite a bit of heat for 10 houses, quite a bit of heat for 10 houses during most of the summer. We also have some larger systems in this project. We have a school in Belgrade that have some very large roof areas where we are going to integrate solar thermal. And then if we look at what has actually been quite successful in Denmark, You can also have large solar thermal fields. In Denmark, we have more than 1 million square meters of solar thermal installed in our district heating systems now. So, this has actually been quite a success. The case is that solar thermal in fields is more cost efficient than integrated it into buildings. On the other hand, if you look at the cities, land is a spare source. So in those cases, it could be better even to integrate them in buildings, even if it's more expensive. Okay, we are gaining some experiences with those integrated solar thermal systems, and one of the places where we do this is in this demonstration facility at the Danish Technological Institute. We got a system. If you look at A, here we got a heat central, then we got a district heating network distributing heat to a nearly zero energy building, where we have a solar thermal integrated, we have a substation, and we have a micro booster. The micro booster was this water heater that is getting some of the heat from district heating and then boosting the temperature with electric heat pump. Then we have another house, C1, also with a substation and micro booster, and we have a small annex where we also have installed a micro booster and a substation. When we are looking at the substation, if you look at this sketch, if we look up here, what we got here is the solar collector system. Then we have some kind of heat exchanger, and then we have a system with a pump that can actually get some heat out of the heat exchanger and delivering it to the district heating system. All what we got down here to the right is what you expect from a normal substation, that you have some delivery of heat to the space heating system and to the domestic hot water system. Okay, so what happens in normal mode, you could say, is that we are taking in district heating, as you will do usually, to deliver space heating and domestic hot water. The water is coming back and go into the return of the district heating system. When the sun starts shining, then the water starts heating up, and when the water is high enough, we have a temperature measurement here to deliver heat to the district heating system. Then we reverse the direction and take in heat from the return pipe and deliver heat back to the system. And to do this, we need to overcome a pressure difference in the network, and we have to control the pump very specifically on that. So this is actually the challenging part of this, to have all this working with the two directions and the pump. This we call a delivery for the supply. But you could also have actually delivery for the return pipe, and we are also investigating that in some other substation designs, and this will create a value. To decide if you should deliver for the supply pipe or the return pipe, you need to look at the value of the heat. In some schemes, you do not want to have a higher return temperature, and then you will it will have more value for the system to deliver to the supply pipe. You also have to look in what part of the network you are. If you are, for instance, at the end of the network, it's not easy to put it into the supply pipe. Then you need to put it into the return pipe, and then you also have to look at the complexity of the installations that you need to do this. So there are some things you have to investigate on site to decide what kind of supply you should do. Okay, so we have tested this this system, and here we have a graph with energy up here, and we have the hours of the day out here on the x-axis, and then we have the main supply of district heating here for this small scheme I showed you before. And then we have at a time of the day the sun starts shining, and we will get some heat injected into the system. But you can see this is, of course, only when the sun is shining. So this is this is not incorporating any storage. But in the system, we actually got small storages in every apartment or every dwelling. We got a storage here of 185 liters. And this is this micro booster I talked about before. So if we look at the tapping of domestic hot water, we got here some tappings during the day. And then when the temperature drops inside the tank, then the tank will start charging. And this is done by charging by district heating. This is what we see here. And then on top, we are supplying some electricity to raise the temperature inside the tank to a sufficient level. Okay, but as you see here, this is actually in some kind of off mode compared to the solar production as we saw before. So we have here the sun is shining during the day, but our consumption is actually outside the period where the sun shines. So actually, to optimize the uptake of the sun, we actually need to move this this charging to another period of the day. And that is what we are working on right now, and what we are going to implement during the summer, that we can actually control this by some price signals, depending on the forecast of the sun and the electricity price. Yeah. So if I should summarize, yeah, what we get out of the RELaTED projects. We are getting some experience with lowering temperature of district heating networks, and that will actually facilitate the uptake of low temperature heat sources, and also the efficiency of some of the sources we are going to use. By introducing those distributed energy resources, we can actually add some production capacities, either for extensions of networks or for completely new district heating areas. One of the experiences we can share already now is that we actually need some kind of standardization of substation design for prosumers, so we can ease the use of the solutions. And then we also think there are some good opportunities in providing smart control and demand-side management in buildings. And because the controllers of, for instance, the microbooster is quite advanced, we can also start aggregating storage capacity and flexibility in the district heating network. So getting coordinating the flexibility of many sources. Yes, I think that was what I will say today.
Wonderful, thank you so much, Mr. Jose Arjona. I invite you to take over on the floor. And meanwhile, I would like to congratulate our speakers, because we have no questions so far. So I think you are very, very clear in your presentations. Yeah, if you could stop sharing first, so that we can take over, that would be wonderful. But if you have a question, no question is stupid, huh? So please just use the chat box. Actually, we could also continue, and maybe some things were not presented yet, so that could be quite valuable.
Good morning.
Good morning.
Do you see my screen?
Yes, yes. You can indeed click on ocultar.
Yeah.
Yeah.
Let me check. Here
Perfect.
it is. Okay.
And if you want to turn on your camera, you can as well.
Okay, perfect. Let me. Yes, it is. Okay. Well, good morning again. My name is José Ignacio Ajona from Sensor Renoval. I'm going to talk to you about well, a similar project regarding district heating cooling. It's the WEDISTRICT project. That is a H2020 project. And within that project, we are working on a system, a new solar system that is also related, also is thought for district heating systems. The WEDISTRICT project is a smart, the name comes from a smart and local renewable energy district heating and cooling solution for sustainable living. As it has already been said, as you know, the heating and cooling buildings and industry in the European Union accounts for 50% of total energy consumption. Of this energy, 70% is generated from fossil fuels. And within WEDISTRICT, our goal is to demonstrate this 100% fossil-free heating and cooling solution for new and existing heating cooling. Within WEDISTRICT, we are well, working with different technologies. We work with 3 different technologies, one low emission biomass. We also have one project with hybridization PV and geothermal, 2 different cooling systems from renewable. We also are participating in this one and in one of the solar technologies. Also, waste recovery from data center. We are working, analyzing also molten salt energy storage, advanced ICT, and of course, we use other conventional technologies. Within the solar technology, we are focused on concentrator technologies, mainly the parabolic trough collector, the Fresnel collector, as you can see here, and a new one that is the Advanced Tracking Concentrator for fixed tilt solar thermal collector. That is the one that we are going to talk to you about more in detail. As expected, main results from WEDISTRICT are this 100% renewable district heating and cooling system, a portfolio of a replicable solution for district heating and cooling system, and we expect also to attain a higher public acceptance for DHC systems. The main data from the WEDISTRICT project is shown here. The project coordinator is Acciona. The funding is almost 15 million euros. We are 22 partners, 9 countries, 4 demo sites, real demo sites, and some virtual demo sites that also we are analyzing different countries. For example, in our case, we are analyzing the virtual demo site in the Canary Islands and 1 demo site in Chile. And 10 technologies, as I said, has been developed. We started in October 19, and we expect to end in March 23. In order to get more information on the WEDISTRICT project, you can go to our, you can follow us on in these links, and also you can subscribe to our community in the WEDISTRICT webpage. Talking about the solar system, the new solar system that we are introducing, that we are testing, we are demonstrating in the WEDISTRICT project. As I told you, is the Advanced Tracking Concentrator for fixed solar thermal collectors. And we think that it suits in your goals of the solution for decarbonizing DHC, although our approach is significantly different. Talking about a little bit about Sensor Renoval is a small company. It was founded in 2008. We are specialists in thermal and PV, in solar thermal and solar PV, and we are focused on industrial application and district heating networks. Regarding the concentrator, we are working with a concentrator that with a fixed tilt collector and with some moving mirrors that tracks the sun. Whenever the sun moves, the apparent movement of the sun, then the mirrors track that movement and then redirect the radiation towards the absorber. This is with the design with two mirrors, and this is the design with one mirror. The design criteria in general is to minimize the solar produced energy cost. That means high productivity, low full installation investment cost, and low operational and maintenance cost. Regarding the concentration description, here you see the main points. As I told you, this concentrator has two components, main components. One is the mirrors, the tracking flat mirrors with one or two tracking flat mirrors and one fixed tilt collector. The design is a low concentration design. The tracking of the movement of the mirrors can do the tracking in the east-west, north-south tracking axis on any other. Also, it gets a quasi-homogeneous distribution of radiation. It doesn't generate peaks on the absorber. As the main technical advantages, you can see here the increased thermal performance, the productivity per square meter is higher, the automatic and simple protection and wind overloads and too high temperatures. That means that whenever there is the velocity, the speed, the velocity of the wind is high, then the mirrors can fall down and protect against that load. And the same with the high temperature. We can also improve the land use the conventional tracking system. We also generate greater operational safety. And that means related to thanks to the automatic and protection against wind and overheating. That means the reduction of structural installation temperature related requirements. The main point here of this design is that it can be adapted to existing thermal products. That means flat plate collectors, vacuum tubal collector, manufactured in large areas. This is important because in that way we are able to get a very good cost of the energy produced because that manufacturing in large areas allows us to have good prices. And in fact, another important point is that it uses well-proven components. The solar collectors with the solar key mark, for example, the mirrors are tempered glass silver mirrors. The tracking devices are similar to those used by millions almost in the PV trackers. And for the control of the tracking and the installation, we use conventional PLCs. Besides that, besides the reduction and the improvements of the concentrator, this concept allows you to reduce significantly the cost of the solar primary circuit. Mainly, it can reduce the piping length, the expansion vessel, because the important point is not to get a good price in the collector, or it is a good price of the energy produced. That means that the cost of the whole system should be the proper one. Then that means that our goal, in fact, is to lower the cost of the produced energy. And these expectations is what is going to be validated in the prototype, especially in the demo site that we are going to implement this application. In our case, the demo site will be in Alcalá. Alcalá is a city quite close to Madrid, and it's in the center of Spain. As the name of our product was difficult to repeat from our partners, we decided to change the name and the logo, and instead to say TCFTC, that means Tracking Concentrator for Fixed Tilt Collectors, we have changed it to WISUN. We smile with the sun, and this smile comes from resembles the shape of the concentrator with the absorber and the mirrors. Regarding the results of our of our prototypes. Here you see, for example, the selected collector. We use, as I told you, a conventional collector, in this case, the vacuity tubular collector from Linuo. And we have tested it in INDEA. It's a research center in Móstoles, quite close to Madrid, in this area, quite close to a small heliostat field that is there already. Here you see some photos of the current situation of the test loop. The main characteristics are here. The nominal aperture area is 122 square meters. The tracking axis slope is 1 degree, almost horizontal. The tracking axis orientation is south-southeast, and we have a storage of 10 square meters. We started this campaign in the beginning of the year, and we expect to, and we have extended this campaign, and we plan to finish it in summer. We have learned a lot on this prototype, and with that lesson learned, we have modified a little bit the drawings of the system, and we will manufacture it the new version to be implemented in the Alcalá demo site. Here, for example, you see the main screen of the control and monitoring systems, where we can follow what the tracking angles and what are the temperatures and flow rates and radiation levels on all the systems. Up to now, we have performed the tracking and operational controls. We also have checked the flow and balance and pressure drop models, and also the structural performance test. And the optical and thermal performance are, well, we have done a lot of them, but it's still underway. We want to continue doing that. But we are focusing mainly on how to improve the mirror cleaning. And we want to implement a constant temperature algorithm, a constant outlet temperature of the solar field algorithm. Also, we are going to test some what is the effect on the PV production in this with the design. Here you have what is the expected results of the efficiency curve. Here, our approach is different as the one you have in the ultra low temperature district heating cooling. It's clear that the best solution is not universal. That can be different in different countries, depending even on the price, for example, of electricity, and depending on the price, for example, on the case of the heat pumps and the small heat pumps of the boosters that you plan to use. In this case, as you can see, we are able to work at quite high temperatures with a very good efficiency. That means that we can work, well, the normal range will be in this range up to 120 degrees C, but typically for district heating, we plan to work in this area on the 80-90 degrees. One point that I want to remark is that this, besides this efficiency curve that is only instantaneous value that at normal incidence of the radiation of the aperture of the collector, this collector has also a very good behavior with different incident angles. But this is what we are now currently testing. Regarding our next activities, we plan to continue with the optical efficiency test, with the instantaneous and daily efficiency, and also with the all the tests related to the formation and torsional performance of the structure. We have prepared a transit-based simulation program specifically for that, a transit system, and that one thing that we are doing, that we are currently doing, is to validate that performance. And we have got quite a good results up to now, although we want to continue doing a further test to validate additionally this simulation. As I told you, also we are working on the new control algorithm and the new cleaning procedures. And we plan to do the manufacturing for the Alcalá demo site of this technology quite likely next month. Next month, perhaps July, depends a little bit on the schedule of the demo site. Summarizing a little bit what are the main applications that we see for this concept are the new and existing low and high temperature district heating and cooling systems and process heat applications for quite a huge range of temperatures applications between, as I told you, between 50 and 120. Well, as an example of what can be done for existing district heating and cooling systems, you can see here, for example, the normal solar installation in the district heating and cooling with flat plate collectors. And the idea here is to boost the performance, to repower the performance of the solar field by installing a mirror in between. With the normal distance of many of the solar fields, for example, in Denmark, that is possible to do it without a significant problem in spring, summer, and autumn. As it was shown, for example, in the previous presentation, the solar system production in the northern climates is quite small. That means that you don't lose much on, and most of the production is done in this period. Of course, in case you need to clean the mirrors, to clean the collectors, or to cut the grass, you can fold the mirrors on top of the collector, and you can do the normal maintenance. Okay, some question, please.
Thank you so much. Well, I think as well, you were very, very clear. Thank you again for your presentation. I don't see any question in the chat box, and actually I see the timing. We only have 3 minutes left. So what I would like to ask my speakers, if they want to join me with their camera, maybe one final word, one final remark that you would like maybe the attendants to take away from your presentations and your projects and the EU policy on this. Anyone would like to start? Yeah, please.
Yeah, good morning again, Clémence. I actually have questions to the presenters of this really very useful project. So the question is, for the RELaTED project, do you see this kind of new technological solutions that are really exceptionally useful for decarbonizing both heating and increasingly cooling? What do you see? Is it easy to implement, for example, in existing networks? Because one of the arguments I hear often is that they have a high temperature network, and so they actually have limited technical possibility to integrate such low temperature solutions for 45 degrees. That's really incredible. Would be an incredible technological breakthrough if we could do that, because it increases efficiency. I really like that you would use a lot of reversible heat pumps that can provide actually several services, heating, cooling, but also the integration of thermal storage is very useful. How do you see the implementation in modernizing the current network? Because obviously to do this in a new network, that's fairly easy. Again, provided that the buildings to which they connect are able to sustain or compatible with such low temperature heating system. But how can we use this kind of technological innovation in the context of existing district heating systems that are basically connected to very inefficient high temperature heating systems in buildings?
Yes, thank you. I think there are more messages. The first one is actually that most district heating systems can lower their supply temperature, and even if they are not lowering it to the levels we are talking about here, it will provide a lot of possibilities. We also have schemes in our system where we, for instance, in Tartu, where we for a whole district is lowering the temperature, the supply temperature by 10 degrees, and that's already a lot, and it also adds to the efficiency of the distributed energy sources, of course. So we are not saying that everybody should go to 45 degrees or even lower. I think we should use the whole palette. We should do what we can do. We should customize solutions for every district heating system. This is one message. The other message is that we need to use distributed resources because we know that, for instance, industry is not typically lying just between the existing district heating plants. So if we need to get that energy into the system, we need solutions for prosumers to easily get that heat into the district heating network. And there are many good examples of that, and also in our project we have the use of industrial surplus heat in some schemes. So do not focus so much on 45 degrees. It's very good, but if you can get from 80 to 70 degrees, it's also good.
Yeah, and if I have still can ask one more question to Jose Ignacio on that was also a very interesting point that, if I understand well, you can basically put the solar collectors on the roof, so it's integrated with the buildings. Thereby, there is a reduction of the land use that is needed for collecting this energy, which is quite a big hurdle for solar thermal to take off. It's currently is very land use intensive. So if I understand well, you can really reduce the surface on which you collect the solar energy, and can be building integrated. And I saw that you had 122 square meter that would be sufficient for actually heating a building itself, or how do you see this land use issue?
Well, the land use, of course, is a critical point in many district heating systems. The question is always what will you have available. The problem with the building integrated system is that typically the cost of the whole system is higher, and that means that the profitability of the solar energy produced is lower. But in that respect, the important point is to know what are your alternatives. When you have a system that is more efficient, that means that to producing the same energy, you require less space. That is always the case. And in our approach, that is why we are going towards solar energy efficient systems. And in fact, the question is that to be able to be efficient with high temperature conventional district heating networks is also one of the key points. We know that to promote a district heating system is something that it's quite slow. That means that the most interesting point is to try to change the existing district heatings from normal conventional district heating to solar-driven energy system. Depending on the country, that efficiency can be reached at high temperature, and it can be reached at lower temperature. because depending on what are, for example, the electricity price is something that it's very, very important. For example, if you have a very, very cheap electricity, you can think of systems that are coupled to, well, to wind electricity or PV electricity or whatever during the night, and then you can use heat pumps. But in the case of countries with higher prices of electricity, clearly you have to choose another solution. And that means that the efficiency point, the economical efficiency point will change from country to country.
So thank you very much. I have a lot of questions. Maybe I get back to the experts bilaterally. I don't want to take up more time of the participants, but very interesting technical solutions.
Welcome. Yeah.
Thank you very much.
Yes, of course. Thank you so much for your question. If you are still available for a couple of more minutes, we had one question in the chat that I think can be of interest for many of us now. It's how market ready are these solutions? I don't know exactly who would like to start.
Yeah, I could start. I think if we look at the solar thermal systems, our approach is actually to do it to do very cheap solutions, not always as efficient as you can get with Jose Ignacio's solutions, but cheap and able to integrate in the buildings. And the two manufacturers we got in the project do already have some solutions working. So I think they are actually close to or even in the market for some of them. About the substation design, I think that's a big effort every time you need to make a substation for those solutions. So this idea about standardizing, getting some perhaps, I don't know, 4, 5, 6 different system designs that you can replicate, I think would be a very good idea. Of course, there have been made substations, but I mean prosumer substations. But I mean that some kind of industrialization of those processes, those systems could be good.
Well, in our case, we consider that we are quite close to be commercially competitive, and again, it depends a lot of on the situation of the country. Spain, for example, has no major. The number of district heating systems in Spain is not big, and in fact, most of them are very, very small. And then the climate is quite different in the north and in the south, for example. Now, that is why within the WEDISTRICT project we are working with so many different technologies, because depending on the situation, perhaps the solution is different. And in all of them, WEDISTRICT is a demonstration project, and that means that we are close to competitiveness. Well, at least is what we intend to demonstrate.
Okay, thank you so much. Well, as we are already a bit late in the timing, unless someone else would like to have a question or would like to share some final thoughts, I think we can close the webinar now. If you all agree. Yes. Wonderful. Thank you so much again to all the participants. As you can see on your screen, you can always check more about the two projects presented, of course, RELaTED, but also WEDISTRICT on the two the websites, and also on social media. So thank you so much for joining today, and I wish you still a very good morning and also a nice afternoon. Goodbye.
Okay. Goodbye to all.
Bye.
Yeah.